Oh.
That's-
Last day, I left us a little bit unsatisfied, if you will. We had a model, and that model was pretty darn impressive. It was allowing us to rank a lot of bulbs, but not all of them. And we found that we kept on having what we call pizza problems, where we were comparing all of a small pizza to half of a large pizza or some fraction of a large pizza. And we found that that our model fell apart. And so today, we're going to build another model, a model for electric voltage in circuits. And, you know, when we were talking about flow and current, it was more flow, more glow. And that just rolls off the tongue. I tried to find something similar to that for the voltage model. This is the best I came up with. More volt, more jolt. If you come up with something better, let me know. And we'll switch off. We're going to start today with a sample problem from an old exam. And so if I could get some help handing these out, anyone, there you go. Going to help me over here. Thank you. Blessing on your head.
Never parallel. Those- I think the CAA might say. You'll be right.
Now, you'll notice that in this problem, you're first asked to rank bulbs. And back when I was young and dumb, before I became old and dumb, I would just ask my students to rank all the bulbs, you know, from brightest to dimmest. And when you've got, you know, 300 plus students and you're grading that late at night, while you're lonely, that turns out to be a mess. And so after a while, I wised up and decided, you know, just have them compare two bulbs at a time. And you know, which of these two bulbs is brighter and why? And after that initial ranking of the bulbs, we ask you to make a change to the circuit. And remember, last day we talked about the fact that there's only 4 ways to change a circuit. You can add a path, remove a path, clutter an existing path, or declutter a path. And each of those has an effect on the circuit. Now, that's the way all of these homework problems are. And the problems in the sample exams that I'll release this weekend, they always start by ranking the bulbs, and then they ask you to make a change to the circuit. So you can expect that on your exam. Let's start out by comparing A and C. And I would encourage you, when making this kind of comparison, to first of all decide what branches are independent of each other. And I would argue that, wrong one. I would argue that A and B are on a network that's independent, and then everything else. Okay, now, when you're setting up the circuit with one of these bars that Clark has made for us. Anything that's going from the red bar down to the black bar is going to be independent of any other branch that's going from the red bar to the black bar. And we'll talk about why that is in just a little bit. Once I've identified my branches, I have to decide how the current's going to divide between the branches. When the current flows out of the battery and gets here, it's got to get back to the battery by either going through this branch or through the other branch. It's either got to go through A or through C. And remember, I told you that your most important tool in your toolbox was being able to look at those two branches and say, which one's harder? Which one has more resistance? And this is how you do it. You draw them the same. You draw the simplest one, A and B, just leave it alone. And then you draw the other one the same. Well, how can I get through this branch and only go through two bulbs? Well, C and D. So this has to be C and this has to be D. And if the current had to split between these, that would be a really simple exam question. You'd say, oh, all those bulbs are the same brightness, Greg. You'd all get 100%, right? Now, what's missing? What's missing is this path with E and F. And again, you never care what it is, you care how it was added. Well, yes, these guys happen to be in series. I don't care. They could be 27 bulbs in series. I don't care. What I care about is how I added them. And I never once picked up my eraser. I never had to break an existing line. I never had to clutter an existing path. I just clipped it on right here and here as a new opportunity for flow. And that means that whatever resistance I have here, we'll call this branch 1 and this branch 2. Whatever resistance I have in branch 1, I have less in branch 2. Now, how do I justify that? How do I argue that when I'm explaining it to someone else, to my friend? Well, I find that some people, when they're starting out with circuits, try to categorize it. Well, this one's more in series and this one's got some parallel in it and also some series. And no, there's just too many different permutations. It's like trying to remember which hand wins in poker. You know, does a full house beat 3 of a? I don't know. Okay. What you do always is to say, this is how you do it every single time. Branch 2 is the same as branch 1, except, and then you put down what's different. In this case, it would be an extra path. Tell me which one's extra. The one with E and F. Okay. And by adding a path, I know that I have lowered the resistance, and that makes the branch on the right the easier branch. And what that means is that C is going to be brighter than A. See if your neighbor just followed all of that. Okay. Now, some terminology. We can say that A is an indicator bulb. Is it an indicator for the battery? No or heck no? No, everything through the battery doesn't have to go through A. But A is an indicator bulb for its branch, branch 1. Like C is an indicator bulb for its branch, branch 2. I could also call B an indicator bulb. Both A and B get all of the current through branch 1. Now, if I compare C and D, tell your neighbor which one's brighter and why. Justify your answer.
Yeah, it won't be pretty bright and steep, but it'll be brighter than.
Okay. I hope what you told your neighbor was C gets all of the current through branch 2, and D just gets part. And so one way of writing that mathematically is that the current through C is equal to the current through D plus the current through E. Okay? And so that means that D has to be brighter than E. Now you could also justify, I'm sorry, C has to be brighter than D. I got ahead of myself. Okay? C has to be brighter than D. It's an all versus part argument. Now we're going to compare D and E. How would you rank those? Which one's brighter? Shout it out. D. D. And your reasoning would be current favors the path of least resistance. Not chooses, but favors the path of least resistance. What about E and F? With one word or less, how would you justify that ranking?
Same.
They're equal, but because they're series. So they are in series. Whatever goes through E has to go through F. There's no other path. Okay, what about B and D? Tell your neighbor which one's brighter, B or D?
We don't know. We don't know.
Okay. Pizza. Little bright, early in the morning for pizza. But that's what we've got. We've got pizza, okay? It turns out that B gets all of a small pizza, and there's the small pizza right there. Whereas D is getting more than half of a large pizza, and there's the large pizza up there. Without knowing how much more current is going through the easy path than through the hard path, I can't make a determination there. I have no numbers. It's a qualitative model. And so my current model fails. Now, by the end of today's lecture, we're going to know what happens in that ranking. We're going to be able to rank those two bulbs very easily. Now, the second half of these problems is that we make a change. And in this particular problem, we unscrew F from its socket. And folks, if you look at a light bulb socket, it's got to touch the terminal at the bottom of the bulb and the terminal at the side of the bulb. And that allows the current to go up into the bulb through the filament and down to the other terminal. But if you take out the bulb, the socket itself looks a whole lot like a gaping hole. Just a big old empty space. Okay, so what does that do to bulb E? We'll go out of order here. What does it do to bulb E? It goes out. Is it shorted out? No or heck no? Yeah, it's just on an incomplete path. It's dark, but it's not shorted out. Okay, a short increases the current through the battery. An incomplete path will decrease the current through the battery. They're very, very different. So let's go back to A. What happens to A? Nothing. We found last day that paths that are parallel across the battery are independent. Anything I do to the branch 2 is going to have no effect whatsoever on branch 1. A and B remain unchanged, okay? What about C? C is the indicator bulb for branch 2. By removing a path, let's go through the reasoning. By removing a path, the resistance of the circuit goes up, the current through the battery goes down, the current through this branch doesn't change, so that means the current through this branch has to go down. And that means C has to get dimmer. See if your neighbor followed all of that reasoning.
Yeah.
Now, I'm just gonna make up some numbers here just to illustrate. I always have people struggling with the fact that, hey, Greg, if you took away a path and the current through the battery goes down, why wouldn't A and B get dimmer? Well, let's just think about that for a minute. With F in there, let's say that we've got a splitting here where 5 amps goes that way and 8 amps goes that way. Okay. Through the battery now, I've got 13 amps. Well, if I take this out and leave the empty socket behind, suddenly this branch looks exactly like that branch. If that branch got 5 amps, then now this one is only going to get 5 amps. And the current through the battery is going to go from 13 amps down to 10 amps. Okay, two things are happening at the same time. The current through the battery goes down, but also the splitting ratio here went from more than half and less than half to 50-50. And that happens for a reason we'll talk about in just a few minutes if you're patient. It happens because this path is independent of that path. Questions on that? Okay. Let's try another problem. This is a problem from an exam. Need my helpers again. Thank you. Yeah, that'd be great. I would like for you to see as many problems as possible before you get to your exam, so that you're just bored silly with these circuit problems, that they all look alike to you.
We take it out, but it's.
Again, this is a problem where we first of all rank the bulbs, and then we turn the page over and we make a change to the circuit, and we ask you how that change affects the brightness of some of the bulbs. Does everyone have one? And raise your hand if you don't have one yet. Okay. Oh, back in the back there. Thank you. Thank you. Thank you. Appreciate it. Thanks. Thank you. Pick up the loaves on the fishes, or these extras? That's yours. Okay. So, let's first of all rank them, A versus B. Shout it out, which one's brighter? A, that's an all versus part, situation. A gets all of the current through the battery, and B gets a fraction. And now we're going to ask, what is that fraction that B gets? Is it 50%, less than 50%, or more than 50%? And so what we're asking is, when the river gets right below A, how does it split? 50-50 or some other way? And the way to answer that, again, is to draw those two paths the same. When the current gets through going through A, it's got a split between B and C. If I draw those two paths the same, this would be B and D, and this would be C and E. And then I ask myself, how would it split if this were the circuit? It would split 50-50. What's missing? Well, bulb F. And I added it in parallel. And so that means that this path, this way is the easy path, and this is the hard path. And so that means that C is going to be brighter than B. Now, if I'm comparing B versus D, that's simple. They're in series, so they're equal. But when I compare D versus E, well, now I've got a problem. D is getting all of the small pizza, all of the less than half current that goes this way, whereas E gets exactly half of the large current. It's a pizza problem. And so we can't answer that. Before the end of this lecture, you're going to see that as a very simple question. Very simple question. Now on the back of the page, we add a connecting wire from point 1 to point 2. And we ask how that's going to change the brightness of different bulbs. Now, you've got to be a little bit nuanced. You've got to be sophisticated in your reasoning. You can't say, well, I added a path, that increases current, all the bulbs get brighter. How many points is that worth?
0.
0. Okay? No, you have to be a little bit more nuanced than that. By adding a path, I know that I increase the current. Where? Through the battery. Through the battery. That's what you know. You increase the current through the battery. Everywhere else can go up, go down, or stay the same. Okay? You have to figure that out. So I've got some questions for you with your clicker. Get your clicker out, please. The first clicker question is, does bulb C go out? Yes, no, I don't know. Okay, last call. Okay. We had only 2 people say, I don't know, but our results suggest that there are more. Okay, another question. Does bulb B go out? Yes, no, or I don't know, with your clicker, please.
I don't know, but.
Okay, last call. Okay, again, 4 people don't know, but we're kind of split on the answer. Here's another tool for your toolbox, and this is a useful one. When you're looking at connections, wire connections, you can move that connection anywhere you like without changing the circuit. As long as you don't cross an element like a bulb or a battery or a switch, or a resistor, you don't change the circuit. And so if I were to move this junction right here, if I were to move it to there, have I changed the circuit? No. If I move it there, have I changed the circuit? No. If I move it there, have I changed the circuit? No. And now we see that we are shorting out B. We are shorting out B. We are not shorting out C. Okay, C doesn't go dark, but B does. B does. So let's answer some questions here. What happens to bulb A when I add that extra path? Shout it out. It gets brighter. It's an indicator bulb, and we've just made it easier for flow in this circuit. What about bulb B? Shorted out. It's shorted out. It's dark and shorted out. What about bulb D? Well, there's 2 things going on. The current through the battery went up, and let's talk about the ratio, the fraction of the current that this branch gets. It used to be the hard path that got less than half. Now it's the easy path that gets more than half. So that means that D's share of the total current went up. Oh, and the total current through the battery also went up. And so that means that D has to get brighter. But when I look at bulb C, I've got a conundrum, because the current in the battery is going up, but C's share just went from more than half to less than half. So now it's getting a smaller share of a bigger total current. I don't know which one of those is going to win. And so my current model fails. Again, in just a few short minutes, you're going to be able to solve that problem. Okay? Questions on that? Yes.
Why is it not change it? Why are you allowed to move the wire after it? Shouldn't it matter what side of the direction you're on?
It does not. It does not. Let's see if we can whoa. Does this look like? Yeah. Does this look like C and E and F and B and D? Okay. So if I need a bulb A, don't I? So let's put, this is bulb A, and we're going to grab this. Oops. Now, I can't reach bulb A up there with my lead, so I'm gonna bring it over here. Is that okay? We call that A. And now if I okay. So you see the C is brighter than B. And if I take a wire and I connect it from right above, let's go back. Right above C. Okay, I'm gonna put it from right above C to right below B. Okay. Now, if I move that, memorize the brightness of everything. See how bright D is and how dark B is? Well, if I move this up here to the junction, did that change anything? Move it here. Move it here. Move it here. Move it here. Whoops. Doesn't change a thing. Now, why? Right now, we don't know. Our model doesn't explain it. 5 minutes, and you'll say, oh, yeah, of course, okay? Now. So, we found a lot of pizza problems where our current model fails. Let's try something else. Let's try something else, okay? Let's try voltage. Now, you remember, voltage, when we say voltage, we mean voltage difference from some point A to some point B. And if we measure the voltage across a battery, if it's a 12-volt battery, we measure 12 volts. And we know that 12 volts is really a fancy way of saying 12 joules for each coulomb that goes from the negative terminal of the battery to the positive terminal of the battery. And we interpret that as energy, electric potential energy, given to each little dump truck, each little coulomb that goes through the battery. If we measure the voltage across that single bulb that's bright, again, we measure 12 volts. And we interpret that as a loss of energy, or really just a transference, transformation into heat and light, other forms of energy. And so our cartoon model is that these coulombs, the red little circles, go around bringing the energy, electrostatic potential energy, to the bulb. And they just go around like that. Okay. Now, what about the currents? Well, the currents are how many of those dump trucks go past any point at any given time. And the currents are the same everywhere in the circuit. What goes around comes around. Okay. Now, if I've got two bulbs in series, the current now is less. I find that those are less bright. If I go back to remind you, that's the brightness of a single bulb. And if I look at two bulbs in series, gotta get this out of there. They're dimmer, but they're the same dimmer, okay? Now, more flow, more glow means that they have less flow than the single bulb, but the same flow as each other. And we know that they're sharing the current like a book. And so the current through the battery went down. We talked about that last day. Now, if I measure the voltage across that battery, I still get 12 volts or 12 joules for each coulomb. And if I measure the voltage across each of the bulbs, I get I get 6 volts across either. Let me demonstrate that for you. The voltage across the battery is going to be from the from this red bar to the black bar. Just a second. Okay, so I get 12.33, 12.34, okay? And now if I measure it across, if these bulbs were identical, I would get have the same reading of over each one, 6.13 and 6.15. Can we all agree that's pretty much the same? Oh, good, thank you. Okay. Now, the way I interpret that in my cartoon head is that these two are sharing the energy like you would share a book. Okay, no, I said that wrong. They're sharing the current the way you'd share a book. How are they sharing the energy? High. Okay. Now, here's my cartoon. The darker the red, the more electrostatic potential energy. The higher they are up on the cliff. Okay, so those up here at the top are at the top of the cliff. These in the middle are halfway down the cliff, and these that are a light shade of pink are at the bottom of the cliff. And you see that the dump trucks just go around delivering the energy as they go. Now, we have said on a number of occasions that voltage is very, very similar conceptually to elevation, the gravitational case. And so let's take a field trip. This is Gallatin Valley. This is where Montana State University is. It's right down here in the valley. And that's our very, very weak imitation of the Y. Okay, it's just an M. And it's all we got. Okay, now we're going to go on this field trip, and we're going to start here on campus, and a magical plane is going to come and pick us all up, and through a process that we cannot possibly fully understand, deliver us on top of that mountain. And in that magical process, delivers to us each on average a gravitational potential energy that is M times G times H. The average mass of a human is 75 kilograms, and that's G, 9.8, we're calling it 10, and the height of that peak is 1,000 meters. And so on average, that plane is delivering 750,000 joules to each person that got on the plane. Are you with me so far? Now, we got to get back to campus. And we notice that the easiest way to get back to campus is along this path. It's called the Ridge. And every year they have a ridge run that I have never participated in. Never. It goes along this ridge and it comes down right across the M and then back along Ralph Street to campus. Okay? Now, what is the change in gravitational potential energy for every person on average that takes that path back to campus? Tell your neighbor. Okay. What goes up must come down. That's what we learned with gravitational problems. And that's what we learned with voltage. Okay. And so the change in gravitational potential energy per person on average is going to be a negative 750 thousand joules. Okay? And because that's the easiest path, nearly all of us are going to go that way. But not Oliver. No. Oliver sees another way. He sees another way to get back to campus, right down the face of that mountain. Okay? And what's going to be the change in gravitational potential energy for Oliver? Yeah, also negative 750,000 joules per person. Okay, and so what we see here is that because this is the easy path, I get more of the people going that way. I get a high current going that way. Whereas this being the harder path, I get fewer people, just Oliver, a small current, if you will. Okay. Do you see it? Do you see an electric circuit there? Let me show you. Pow! Now, I would ask you, where on that diagram do you find the plane, the airplane? Where's the plane? Yeah, the battery. Just like the plane was delivering potential energy to every person, the battery delivers electric potential energy to each coulomb, Now, how bright are the bulbs? Well, we've seen this circuit before. The bulb on the left is really bright, same brightness as if it were the only bulb in the circuit. And these two act as if they are just like this, as if they didn't even know about that one on the left. Now, if I measure the voltage across the battery, I still get 12 volts or 12 joules for each coulomb. If I measure the voltage across the single bulb, I get, we see this in this week's tutorial, 12 volts. And if I measure it across either one of those dimmer bulbs, I get 6 volts. So here's the big idea. The battery delivers or takes each coulomb up to the top of the cliff. The change in electric potential energy between this positive terminal of the battery and this negative terminal of the battery is 12 volts. And it doesn't matter which path you come down, whether you come down this path or whether you come down this path, the change in voltage is going to be 6 volts. How many? 12. Thank you. 12 volts. Now, if you think of that voltage difference as a pressure difference, essentially high pressure here and a low pressure there, it's just pushing, it's trying to drive current, okay? And if I've got the same pressure difference from here to here, regardless of what I do to that branch over there, they're independent of each other. Does that make sense? Suddenly it makes, it's not a mystery anymore why these are independent of each other, why they act as if they have their own battery. Because they've got a direct connection to the positive terminal of the battery, a direct connection to the negative terminal of the battery. They've got 12 volts across them. See if your neighbor is anywhere near the bus,
It's like double. It's like.
Okay,
Yeah.
now just because we came down the ridge and came down 1,000 meters doesn't mean that we used up the 1,000 meters. When Oliver has to come down that cliff, he's still got 1,000 meters to come down, okay? Regardless of which path you take from the top of the mountain to the bottom of the mountain, your change in elevation is still going to be a negative 1,000 meters. You don't use it up along one path. The same thing is true with voltage. Every path that goes from one side of the battery to the other is going to have a drop in voltage that's equal to the battery voltage. But what about the currents? Well, again, this was the easy path, so all of us in the class went that way, except for Oliver that went the hard way. But we all went up on the airplane. Those of us that went the easy path and Oliver, we all went up on the airplane. So that's the sum of the two currents. Now, this is the voltage model, and after learning the current model, it seems pretty darn simple. Voltage is just how much energy each coulomb of charge gains in the battery or loses in the bulb or other elements, okay? And what we find over and over again is that for identical bulbs made at the same factory by the same worker on the same day, the more volts I have across the bulb, the brighter it is. Now, we used to say, well, if there's two bulbs and one of them's brighter than the other, this one's got more flow going through it. Well, now we can say, if there's two bulbs and one of them's brighter, there's more volts across it. And sure enough, if I measure that, the voltage across this bright bulb is, it turns itself off. That's what I find. Okay. So the voltage across this bright bulb is 10 volts. The voltage across this one we already know is 6 volts. 6 volts. Okay. So the brighter bulb has more volts across it and more flow through it. Those are not disconnected. It's the greater push, the greater pressure difference across this bulb that's responsible for driving more flow through it. Okay? Now I want you to be really, really careful with your language so you don't get yourself confused. Whenever you're talking about current through the bulb, through the wires, through the battery, it's always through. But you never, ever, ever, ever talk about voltage through. The voltage doesn't go anywhere. It's a pressure difference from point A to point B. So we talk about the voltage across bulb C, the voltage across bulb B, the voltage across the battery, from one side to the other, a pressure difference. Check on your neighbor again. Do a buddy check.
Like how much is that I have.
Okay, let's go on with our voltage model. We say more volt, more jolt, because I don't have any better way of saying it. We also find that what goes up must come down, that any voltage rise across the battery has to be equaled by the drops around any loop. Any loop from one side of the battery to the other has to have the same drop as the battery has a rise. If it's a 12-volt battery, I've got a 12-volt drop around any loop. How many of you watched this week's tutorial video so far? Okay, not many of you. If you go and watch that, that'll really, really help clarify this model. Now, let's see if we understand the model. We've got a circuit that we have seen before, and we've got a single bulb in series with a network of two bulbs in parallel. And we know that that top bulb is the indicator bulb, and it's going to be the brightest of the bulbs. And I represent it this way. And my question is, if I call that bulb A and I measure the voltage across that bulb, will I get something greater than 6 volts, equal to 6 volts, or less than 6 volts? let's use our clickers on that question. Now you can click. Okay, last call, please. Okay. It looks like greater than 6 volts wins, but we have 46 choosing equal 6 volts. Let's talk about that. I suspect that we're using different models. That right now we haven't kind of come to an agreement about what our model is. Some of us are taking the voltage across A plus the voltage across B plus the voltage across C and setting that equal to 12 volts. Others of us are just taking the voltage across A and the voltage across B, and that has to add up to 12 volts. Tell your neighbor which of those you are using, which is your model.
Neither.
Okay. You remember, we said that any single path from one side of the battery to the other has to drop 12 volts. Well, imagine that Fred, that blueberry that we painted green, he's trying to make his journey from the positive terminal of the battery to the negative terminal of the battery. He's got to go through bulb A. He's got it. But then he's got to choose. He either goes through B or he goes through C, but not both. And so that means this is the correct model. Any one path has to add up to the 12 volts of the battery. And the one path is either A plus B or A plus C. But it's not this, okay? And then if I know that A and B have to add up to 12, and the brighter the bulb, the bigger the share, well, that means that A has to have greater than 6 volts and B has to have less than 6 volts. I'm going to make up a number here, okay? I'm going to say that A has 8 volts. I just made that up, okay? How many volts does B have? 4. How about C? Whoa. 8 plus 4 plus 4, that's 16. Whoa. Can it be more than 12? Yes, yes, it can. It has to be 12 along any single path. Now, as a result of this rule, anything that's in parallel always has to have the same voltage across it. And if we go to the gravitational case, if you're starting at the same point on the mountain and ending at the same parking lot, you're both coming down, regardless of which path you choose, you're both coming down the same elevation difference. Are you not? You are. Okay? It's the same way with voltage. If you start at the same place and end at the same place, regardless of which path you take, you have the same drop in voltage. Now, another way of looking at voltage is looking at things that are in series with each other. And I would ask you, is bulb A in series with bulb B? Yes or no?
No.
No or heck no?
Heck no.
Heck no. Well, some of you are saying, well, I don't know, that looks like a pretty straight path there. It looks like just poof. That's not what series means. What series means is that everything that goes through A has to go through B. And everything that goes through B is the only thing that goes through A. Okay, what is A in series with? This whole network. And that's why I put boxes around them. This box is in series with that box. And that means that this battery has to somehow get the same number of coulombs through the top box each second as it gets through the bottom box each second. Okay, it's gotta push those coulombs through those boxes. And if I look at the voltage across those boxes, I get a big voltage across the top box. If I ask myself which of those boxes is harder to get through, well, I know that two paths is easier than one path. And so that's going to be, the top box is going to be the harder box to get through. And so if we think of the 12 volts of the battery as the battery's technical term, okay, how are we going to divide up that 12 volts of to get the coulombs through the boxes? I got to use more of it to get through the harder box and less of it through the easier box. That's how we think of voltage. Now, for series network, and folks, I wish I had written this in capital letters and red. This is only for series networks. The voltage drop is greater across the larger R. What about parallel networks? Which one has the bigger voltage drop, the larger R or the smaller R? Trick question. It's always the same. Parallel networks always have the same voltage drop across them, regardless of the resistance. Regardless of the resistance. Okay, let's go back and solve our pizza problems. Okay. If I have a 12-volt battery and these two bolts here have 12 volts across them, and they're the same brightness, we saw they were the same brightness, they must have 6 volts and 6 volts. By our current model, we said that C had to be brighter than A. Well, if A has 6 volts across it, C has to have more than 6 volts across it. And that means that D has to have less than 6 volts, because whatever I have across C plus whatever I have across D has to add up to 12. Okay, if C has 9, D has 3. So suddenly it's not a pizza problem anymore. Now I can see that B has to be brighter than D because it's got more volts across it. Questions on that problem? Okay. This is the circuit that we had last day. I've got it on the board, but I changed the lettering here for the other problem. Let's put the correct letters up here. This is going to now be A, B, C, D, and E. And again, we found that this branch on the left was independent of that branch over there. We could make any change we wanted over here. It didn't affect anything over here. Again, we could make any change over here and it doesn't affect anything over there. And the key is that I've got 12 volts across this branch and 12 volts across that branch, independent of what happens to the other branch. That's the explanation for our observation last day. That's why they're independent, is that they have 12 volts across them if they're connected to both sides of the battery. Now, if we put that indicator bulb in there, let's go ahead and do that. First of all, we know that by putting that indicator bulb in there, we're going to add some more resistance. We're going to lower the current through the battery, and that's going to affect all of our bulbs here, making them dimmer. But you can see that A is still brighter than D. D, I can just barely see a tiny glimmer there, but I can see A is glowing. So the question is, what's going to happen to the brightness of A when I close the switch? Well, last day it was a pizza problem. A is suddenly getting a bigger share. I'm sorry. When I close the switch, A is getting a smaller share of more current through the battery. So let's talk about what's going to happen when I close that switch. I close the switch. What does that do to the current through the battery? Shout it out. Increases it. What does that do to the brightness of that indicator bulb? It's brighter. What does that do to the voltage across the indicator bulb? Brighter bulb has bigger voltage. Remember, it's got to be 12 volts from one side of the battery to the other side of the battery through any path. That means the voltage across the indicator plus the voltage across A plus the voltage across B has to be 12 volts. So if the indicator gets brighter, A has to get dimmer. And B and C each get half the current through A, so if A gets dimmer, they each get dimmer as well. See if your neighbor understood the answer to that pizza problem. Okay. Let's see if that's what happened. Our model predicts that A is going to get dimmer and D is going to get brighter. Okay, it also suggests that the indicator bulb is going to get brighter. So I'm going to short out E by closing the switch. Okay, first of all, watch A get dimmer. Did it get dimmer? Yeah, it did. Yes. Now watch D get brighter. Did it get brighter? Yes, say yes. Now, what about the indicator bulb? It's hard to say. It was so bright before that we can't tell. Okay. Good, good, good. There it is. Okay. So bulb A gets dimmer. Let's go to this one. We found a pizza problem when we tried to compare D to E. D was getting all of the small pizza. E was getting exactly half of the large pizza. Now, here's how you would use the voltage model to answer that pizza problem. I would pick a path from some starting point to some ending point that goes through D. And I would take a second path. I'm sorry for these little jags there. They weren't there. Bill Gates put them there. Okay. I have to start at the same starting point and the same ending point and go through the other bulb. Remember, I'm trying to compare D and E. Now, I know that the voltage drops along those two paths, the red one and the blue one, have to be the same. So I can say the voltage drop across B plus the voltage drop across D, that's this red path, has to equal the voltage drop across C plus the voltage drop across E. That's this blue path. Now, if I want to compare D and E, I first of all have to compare the other two. Okay. If the blue team wins here, but overall it's a tie, then the red team has to win there. Okay. If C is brighter than B, then D has to be brighter than E. You see how that works? Okay. I'm trying to find another analogy that would work. Okay, let's see. You three come up. Okay. We're a team. What's your name?
Charlie.
Charlie and I are a team, and you two are a team.
Cameron.
Cameron and
Truly.
Truman. Okay, so we're a team, and each team gets $1,000. And we split it between ourselves. Charlie and I split it, and Cameron and Truman split it, so that no one can see, okay? But then Truman and I step forward and empty our pockets. And it turns out that Truman wins. Okay, he's got more money in his pocket than I do. Do we know how it's gonna go for them? Yes, we do. Yes, because we all started with $1,000 and it's a zero-sum game. Okay, thank you, gentlemen. Okay. Now, let's talk about this question here. Why doesn't it matter if I move that junction from here to here to here to here to here to here? It doesn't matter because there's no voltage change across the wire if it's a perfect wire. And so if I go from here to here, I've got the same pressure difference across that wire than I do when it's here to here. And so voltage is the answer why I can move that connection anywhere along a wire. Because the current doesn't have eyeballs, okay? It just knows how much push there is, how much pressure difference there is from one side of the wire to the other. And that determines the flow through the wire. Check that your neighbor's on the bus, please. Now, we've got 7 minutes. First of all, we were confused about what would happen to bulb C. We weren't trying to compare it to any other bulb. We just wanted to know when we made that change by shorting out B, what happens to bulb C? Does it get brighter, get dimmer, or stay the same? Well, to answer those questions, we use our voltage model a little differently. We take a path that goes from the positive terminal to the negative terminal through the bulb we're interested in this case, bulb C. And all of those voltages have to add up to the 12 volts of the battery. And then we figure out what happens to C by looking at the other bulbs. Well, I know that adding a path makes the indicator bulb go brighter. So that voltage gets bigger. I know that E is always going to get half the current that C has, so they have to go the same direction. If C gets brighter, E gets brighter. If C gets dimmer, E gets dimmer. So they have to both decrease in order for that equation to still equal 12 volts. Okay? Now, questions? Here's a summary. When using the voltage model, we put things in boxes that are in series with each other. And the voltage for series elements divides. If the voltage divides equally, that means that the resistances in the boxes are the same. But if they're not the same, the voltage drop is greater across, is it greater or the lesser R? The greater R. Okay. Now, this is a homework problem for tutorial 5. And I just want to get you started on it. And that way, when you get to your homework, you won't be overwhelmed. Okay. We have this circuit, and we would like to rank the bulbs using the current model first. So be the river and rank those bulbs. Tell your neighbor which one's brightest, second brightest, third brightest.
Okay, 6 is the brightest. It's 4 and 5. And then more people, but then they're going to go out in a harder path. That they're going to get nice flat three connected right and then 1 and 2. The 6.
Okay, all the current goes through 6. So it's gonna be the brightest. Let's go around counterclockwise. When it gets here, it splits 50-50 or some other way. 50-50, so they each get half the current. It comes back together, it splits here 50-50 or some other way. So this one gets more than half, so it's gonna be the second brightest. And then 4 and 5 are going to be equal because they're equivalent paths. And they're gonna be brighter than 1, which is equal to 2, and that's because they're series. And this is because they're equal paths. Parallel paths. Okay. So now, if I were to ask you to use the voltage model to rank those bulbs, normally you get to use whichever model you're most comfortable with. And if you get to a pizza problem, switch models, okay? But in this case, we're tying your hand behind your back and saying you can't use the current model. So what's the first thing we do with the voltage model? We put them in boxes. We ask ourselves, what's in series? And what's in series is that box with 6 in it, with that network with 4 and 5, and that network with 1, 2, and 3. And then we ask ourselves, which box is hardest to get through? Which one is going to require the bigger share of the battery? Yeah, 6 is going to be the biggest resistance. The second biggest is going to be that top box, and the middle box is the smallest. Okay, Papa bear, Mama bear, baby bear. Okay, and that's the way the voltage is going to be divided up. Folks, we've got a devotional today, so rather than finishing this problem, we'll finish it on Tuesday when you come back. Go to devotional.
Thursday. Wow.
I love you people. I'm not trying to make your life miserable.